NTU World of Wisdom. Welcome to High Impact Thesis. In this podcast, we speak with researchers from various scientific fields to talk about the motivation, goal, and potential impact of their research. We also want to give you a sense of how a PhD is carried out with an emphasis on the PH, the philosophical aspects involved in pursuing a PhD.
Hello, everyone. Welcome to another episode of the High Impact Thesis podcast. Today we have Shilpa Manandhar. She's a researcher at A-Star, and we're looking forward to hearing from her about her research and her research journey and what she has discovered during her PhD and maybe her postdoc as well. Welcome, Shilpa.
Thank you, Ahmed, for giving me this opportunity to join you in. I'm very happy to share my experiences with you all.
So to start, we'd like maybe just for you to introduce yourself to the audience and give us a little bit background on your research area and what you do.
Sure. So as Ahmed just mentioned, I did my PhD, and I did my PhD from NTU. I joined it in 2014, and I completed in 2018. So 4 years of PhD, and my topic for my PhD was GPS-derived precipitable water vapor for rainfall forecasting. So in general terms, my basic objective was to devise a new algorithm for prediction of rainfall, and it was based on GPS. So GPS is global positioning system. So when people generally hear about GPS, we know about that it's for locationing and it's for positioning. But my objective was to look at how these signals from GPS can be used in deriving so-called precipitable water vapor. And from there, I had to find algorithms to get rainfall forecasting. So in Singapore, Singapore is basically a tropical country. So being a tropical country, there is lots of rain as experienced by all of us, I think, over the years. So it's like a rainy place. And there are other instruments and other devices as well, which are being used to get rainfall data, rainfall forecasting and all. But the advantage of GPS is, as we know, our phone also has a GPS receiver, right? So GPS is growing rapidly, and not only GPS, but now it's called GNNS, which means that it includes GPS, it includes Chinese satellites like Beidou, it includes Russian satellites, and many more. So that means it's growing in space. So therefore, if we can use GPS to do something like rainfall forecasting, then it can in a way substitute all those other existing devices, and which comes to be cost effective, and it also has a potential for R&D. So this was all about my PhD that I did. And now after my PhD, I did 1 year of postdoc in NTU itself in the same field. And now I'm with A-Star, which is a government agency in Singapore. And a part of my work is also continuing what I did in my PhD, but I'm also looking at other parts in my current work, which is also dealing with GPS. Yes.
And can you tell us a little bit more about what got you into the field in the first place?
Actually, when I came, to be very frank, so I did my bachelor's back in my country, which is Nepal. And after I did my bachelor's, I was looking for opportunities to go abroad to do my master's or my PhD, right? So I was applying to lots of universities, as we do. And I applied to NTU as well. And so my professor here, she actually, because I come from a triple E background, right, and specialization in communication. So she interviewed me, and she asked me if I am interested in a microwave-related project. And I was like, okay, I'm like, it's okay. And then they also offered me PhD direct after bachelor's, right, which seemed to be a good opportunity for me at that time. So I was like, okay, let's try it. So after I came here, then I got into this project. She offered me 2 or 3 choices, and I thought that this one is interesting because to me at that time, like all the other projects that she offered to me was like vague, but this one I could relate because rainfall forecasting, right? So I could like in a way kind of get it. Okay, I need to do this. I could visualize. So I thought, okay, this project seems interesting. So I joined in.
Interesting. And I would never link GPS to rainfall forecasting. That sounds really interesting.
Yes. I can give you a little background. So we have GPS satellites in space, right? So let's say there is one satellite and there is one receiver, right? So what's the communication? It's just the microwave communication between satellite and a receiver, right? So when the signals pass from satellite to a receiver, it will pass through many things. Like it's 22,000 kilometers space between the two. So when it passes, it will pass through ionosphere and it will pass to troposphere, right? So in ionosphere and troposphere, what happens is basically there are different elements because of which the signal will not pass straight, but it will bend because of the refractive index difference, right? So when it passes through troposphere, there is water vapor molecule around atmosphere. So this water vapor molecules also changes the refractivity, and therefore the signal gets bent. So my research was to look at how much the water vapor content is causing that bend. So that bend is equivalent to extra delay to the signal, right? So I have to find this extra delay, and then I correlate this delay with the water vapor content. Yeah, so this is a gist.
And do you have an idea how old this technique is? Is it recent or it's been done for?
So basically, this technique of getting the delay is very old because people used to do ray tracing, right? And what they used to do for ray tracing is a radiosonde. Have you heard about it? It's a balloon. It's a balloon that is flown up in the air, right? So it has a transmitter. So as it goes up in the air, it will transmit the humidity, temperature, pressure, all these values at different heights. So after crossing certain height, it will burst and it will just flow away, right? So this is the technique that is used to get the temperature parameters and other parameters in the atmosphere, because people have been doing this rain forecasting and weather forecasting for a long time, right? But with GPS, it's I think 10 years plus old. Yeah.
I see. Interesting.
So I have a question. You mentioned something about the clouds bending the waves, right? The radio waves. Does this interfere with the normal functioning of GPS or usually?
Yes, it does. So you are talking about like location, right? Positioning, right?
Yeah, positioning.
Yes,
system.
it does. So there are interesting papers which talks about this, how much bend and how much positioning accuracy you need, right? But actually, if you think about it, when we talk about positioning, we do not talk about centimeter level, right? I mean, you just want to be around an area. When you are driving also, you just want to be around an area. You do not need to be like 1 centimeter precise, like where you are, right? So because this delay that I'm talking about is very less, all right? So this less delay doesn't propagate to a very wide range of position. But if you're talking about centimeter level positioning, then this delay becomes very, very important. So it's like, if you're talking about meter range of positioning, then this might not be so important. But if it's centimeter level, then it's important. Yeah.
I see.
But then also when you are using maps, Google Maps and everything, right? What happens is after you get GPS positioning, they do something called map matching. So it's like they already know the existing maps, right? So when you get GPS signals, they will map you back into the road so that you are not driving on the hills,
sidewalk,
driving on the houses, right? They map you back on the road. Because they already know the maps. So it's called map matching technique. Yeah.
And do you use the data you get, do you use it in congregation with other data from other techniques, or is the technique by itself enough?
Yeah, I understand. So initially during my first 2.5 or first 3 years of PhD, I was just using GPS data because it was a lot for me to analyze the data first, to get used to the system and to find how this delay works, right? So I couldn't use any other. But after 2.5 years, around third year of my PhD, I could get it done. So actually after that, I used machine learning techniques to actually incorporate temperature, pressure, and other data into it to improve the prediction of my algorithm. So one of my papers was just purely using GPS derived signals to do the forecasting. But in the later years of my PhD, I used the algorithms to incorporate other parameters as well.
Right. I guess maybe it's also a good chance now to give the audience a little bit of an idea of the GPS itself and how it works, if you may. Yeah.
So you want to know how GPS works?
Yes, for positioning.
For positioning, okay. So GPS is basically based on trilateration, if you know about it. So what happens is if you have one satellite and the idea is to know the position of a receiver, right? So if you have one satellite, then you cannot get the position of a receiver. So if you have three satellites in view and there is a receiver, right, then you can do trilateration to find position of the receiver. But what happens with GPS is even three satellites is not enough. Why? Because GPS and the receiver, how it works is GPS sends the signal, receiver receives the signal, right? Then there is a time difference. So using that time difference, you will find how far this satellite is based on the receiver. Then you will find this distance with respect to three other satellites and you will do the trilateration. But in case of GPS, what happens if the receiver clock and the transmitter clock are not synced, right? So there will be a difference of seconds, right? So 1 second difference is actually very, very high. It will equivalent to kilometers of difference, right? So your receiver of GPS and clock needs to be synchronized and the difference cannot be more than nanoseconds. So it should be in that level, right? So for satellites, it's quite good because they are on board with atomic clocks, so-called atomic clocks, which are very highly stable and doesn't drift away. But GPS receivers cannot be equipped with atomic clocks, right? You can imagine our phones do not have atomic clocks. So what happens is there is one more parameter, which is like receiver clock bias, which comes into fact that you have to take factor of the thing that the receiver clock bias can cause some error. So to accommodate that thing into the equation, we need 4 different satellites in view at once so that the receiver positioning can be done, because 3 satellites are for X, Y, and Z, and the 4th one is for receiver clock bias, right? So solving the 4 simultaneous equation at once, we can get the position of receiver. So we get X, Y, Z, and we get receiver clock bias. So this is how, in general, the GPS receiver functions. Yeah.
The reason I ask is because I also maybe I wanted you to just talk about the system, the established system by itself, and now maybe you can tell us where do you come in as rainfall forecasting, where I think your part more related to the receiver.
Yes.
And then maybe you can tell us more.
Yeah. So as I told you, it's the same system that is used for locationing and also for my part of prediction of rainfall, because the system is same, the receiver is same, the signal delays are the same, right? So what happens at the receiver is after receiving the signals, we use a software which is provided by NASA, which is a Linux-based software, which is called Gypsy OSC software, right? So we need to get used to how the software is used. So this software solves equations basically to get the values of signal delays and to get the values of pseudo range. So this pseudo range is actually distance between receiver and different satellites, right? So, and just now I said that 4 satellites are needed to be visible to do the solution, but in an actual scenario, if it's a very open sky, there are no buildings, then you can see about 8 to 12 satellites up in the sky at one time, right? So now you can see that from 8 to 12 different satellites, I have 12 different signals that is being received by the receiver, right? So for each signal, I can find how much is the delay there. And for each signal, I can find how much delay is coming from due to the water vapor content in that path. So during my research, I use this software and then I do post-analysis using MATLAB and Python to get the values. And then what I do is we have a weather station. If you know, weather stations are small portable devices that record the rainfall, because I need the ground truth values, right, to compare with something. I cannot just say, oh, rain is happening and do not compare with anything. So I have these weather stations which gives me the ground truth values, right? Then after I get 12 different paths, 12 different water vapor content of the path, I actually have to validate it against the rainfall data that I'm getting with weather station, and then I correlate how much is my prediction results are. Yeah.
Mm-hmm. I have a question about like how does this system differ from the weather forecast satellites? I believe there are some satellites which are dedicated for studying weather and clouds and so on. So how does it differ from those?
Okay, so first difference here is GPS satellites are way much, I mean, like the other satellites which are weather satellites, right? Those satellites are sometimes geostationary, which means that they are, you see it every time on top of a place, meaning that you know about geostationary satellites.
It moves with the Earth, basically.
Yes, it moves with the speed of the Earth, right? So it's always seen at the same time, at the same place. But other satellites like these GPS satellites are not that, because they are not meant for weather forecasting. They are meant for positioning, right? But we come here to find a way to find its use in weather forecasting, so that we do not have to send more geostationary satellites up in the space in a way, right? If these satellites which are already there can solve your problem, then you don't need to send other geostationary satellites up, right? So this is one of the advantages. So this the aim is also to prove that, like GPS can be used, and this is one of the added advantages on top of positioning. So that's the thing. And for this weather satellites, right, I have also worked with weather satellites data, because in our research, people will ask, right, like you just asked me, when I try to publish a paper, they will ask me, why didn't you compare your results with CloudSats? CloudSats are those satellites which are sent just to do the weather forecasting. And then they have this TRMM satellites, which are for tropical rainfall measurements, right? So they will ask to compare these data. So one of the problems that I see in these satellites for weather is like, what they do is they send the signal, and then they will read the reflection from the ground. So if it's coming from the ground, then they say that the thing is relatively clear. But if it's reflected from thick layer of clouds, then they say that, oh, it's cloudy, right? Or if it's reflected by rainfall, then they say that it's rainy. So it's depending upon how much reflection they are getting, how much dBz they are getting as a reflection. They define what's the level of weather on surface of the Earth. But for us, it's like not based on reflection, but it's one way. So we receive and then we do the analysis. Few differences. Yeah.
I see. Would it be correct to say that maybe another advantage of using this approach is that the GPS satellites are more abundant and might cover more surface area compared to the...
Yes,
would that be right?
Yeah, true, exactly.
Mm.
Okay, so I also wanted to know about the kind of the prediction horizon. Like, how far in the future are you able to predict using this technique?
It's a very good and nice question. So one thing that depends on is the data that's available to you as well. Because if, let's say, you are available, you have data which is 1 hour sparse, then you need to do something like interpolation to see how far you can predict, right? But 1 hour would be the best scenario, because you have the actual data in 1 hour span, right? For us, the GPS data is not a problem, because we can process the data every 5 minutes apart. And the problem we had was rain data, because I need ground truth data to do the prediction, right? So weather station actually can give very nice resolution, which is 1 minute apart. So using my 5-minute GPS data and 1 minute rain data, my prediction algorithm was from 15 minutes to 1 hour. So actually, my study, we focused on near real-time prediction of rain. Why? Because we've already seen long-term prediction of rain, like on weather apps. You can see that 24 hours of prediction, right? So we wanted to see like how good it works for near forecasting as well. So we did from 15 minutes to 1 hour, and the problem. Now I can share some of the problem using this. When you work in weather field is to get the data actually, because GPS, as Mohammed also mentioned, is already there, right? So I can get GPS data for any place you want me to process. I can do it. But the problem is I don't have rain data for that place. So I cannot basically do my prediction using only GPS because I have to verify the results, right? So one of the problems I had was this, and then I couldn't only write papers or develop an algorithm only for Singapore, right? Because it would be very smaller audience for my research, no? So what I did was I extended it for tropical region at least. So what we had collaboration with few labs in Brazil. So I got data from Brazil as well, but the data from them was not 1 minute apart, but it was 10 minutes apart. But actually 10 minutes was also good because I had my window from 15 minutes to 1 hour, right? So I could use that data. So I did my verification of my algorithm for 2 stations from Brazil, 1 station from Singapore, and 1 station from India. So all those stations are from tropical region. That's why my thesis was somehow like focused to the tropical area. And one of the biggest issue I couldn't do for other reasons was this data availability. Yeah.
Mm.
Yeah. For GPS, no problem, but for rain, no.
Yeah.
So yeah, one more thing to add was for this rain, right? There are these satellites that I just mentioned, TRMM, which is like tropical rainfall monitoring, right? So they give you these satellites actually give you the rainfall data using the geostationary satellites, right? But the temporal resolution is very bad. One data you get after every 6 hours. Yeah. So the resolution is 4 data points per day.
Mm. Yeah, that's quite the
sparse. Yeah.
Window. Yeah. And what about the geographical area that you can predict for? Like how big of an area can you predict for? So we talked about time, but what about space?
Yeah. So for Singapore, I think I used about 3 stations within Singapore. One was NTU, one is NUS, and one is from Manado. So actually, as I mentioned, right? So this is a receiver. There are the satellites that are there, right? So it's not actually one line, but it forms a cone. If you can imagine. So it's different satellites around, right? So it's a cone. So it's based on what elevation of satellites is available at the time. So it's hugely dependent on that. But as I have done study for a few years of data, so I've seen that the minimum elevation angles that it can go is up to 5 degrees, right? But the availability of satellite for those smaller elevation angle is very less. So it's about 25 kilometers around the receiver.
Oh, wow. That is... Am I right to assume that half of the area of Singapore?
Yeah, because it's very small.
That's true.
So that would give you a spatial resolution of around 20 kilometers?
Yes.
Like you can say, for example, there will be rain on this area, but not in this area, with the resolution of... okay. All right. I guess now we can move on to the next point. Okay, so now we had a good introduction about your research field in general. Now we'd like to move on to more detailed view into your own personal work and with more details and elaborations. So if you can give us a sense of your day-to-day research activities and what kind of, what are the core objectives that you are focusing on right now, recently, and what kind of tools you use and so on. So if you can share with us some of that.
Sure. So my recent work and my PhD is somehow related, but not actually overlapped. So I can share in 2 parts. So when I was doing my PhD, my main focus was rainfall forecasting, right? So I had to deal with this Gypsy software. So every day, like initially 5-6 months, I got I took some time to get used to this new software that I was being introduced to, and it was Linux based, so I had to learn Linux as well because previously I was not familiar with it. So I was doing that, and then after I got used to the software, was quite easy because after that was post analysis was using MATLAB and Python, which is relatively simpler. And and apart from that, I also had to look at different GPS receivers. So the GPS receivers, so two kinds I had to look. One was a simpler portable one, which is known as U-Blocks. And the other one is a bigger one, which is more relatively stable with good clocks in the receiver. So I had to compare the results for both different types of receivers as well about their performances. And so apart from that, there was no much hardware involved in my research during PhD. I was more into software. Yeah, and after my PhD, now the place where I'm working, A-Star, it's basically related to GPS, but I'm more focused on time rather than focused on weather forecasting. So as I gave you a hint already that the atomic clocks are important, right? So I am involved in time and frequency lab in A-Star. So the main function of time and frequency lab is to maintain the UTC. If you know, UTC is a coordinated universal time, right? So coordinated universal time is basically maintained by BIPM, which is Bureau of International Weights and Measurement, located in France. So what they do is to publish this UTC, they need time information from different labs around the world. So there are different labs, they keep their own timings. And in Singapore, the national lab is our center, which is National Meteorology Center. So our National Meteorology Center keeps the time based on atomic clocks, and then we send it to BIPM regularly, like every 5 days. And then BIPM takes into account of all those information from different labs, and then they produce this UTC, which is universally coordinated time, right? And so my role here is basically to maintain the cesium clocks and hydrogen maser clocks in our lab. And it's been 1 year that I'm attached to NMC, and I'm still learning about these different types of clocks, and it's quite different from my PhD, so it's quite a bit challenging, but very nice and interesting. Yeah.
And these are atomic clocks, right? The ones you use.
Yep.
So
yes.
How do they function exactly? Because I have no idea how to.
So it's basically when atoms transit from one state to another, the time that it takes is translated to seconds.
Okay, I see.
So it depends on which atoms you are using. The stability of the clocks are defined. Yeah.
Right.
So how are you using the satellites, the GPS satellites right now? Are you still using the data from the satellites?
Yeah, I do use the data from the satellite. Yeah.
So how does that, because the clocks you mentioned, I know that there are already atomic clocks in the satellites, but you mentioned clocks that you have in the lab, right?
Yes.
So are you making sure that time is the same, or?
Yeah, because in the labs, now in this lab, we have hydrogen atoms and cesium clocks. So cesium and hydrogens are those clocks which are actually boarded on satellite as well. So they are super stable atomic clocks. That's why we are licensed to do the timekeeping. Yeah.
Okay. Also, can you share with us why is timekeeping an issue here? Because I understand these atomic clocks are very precise and very accurate. So why does it require some extra effort to maintain the, I don't know.
So I can share. For example, financial applications. So there is a share market, right? Stock markets, right? So for the stock, I think time is very, very important, right? Yeah, and everybody around the world needs to be in the same time. You cannot be differentiated even by milliseconds or microseconds, because the time there is very, very important. So what happens if my time here in Singapore and somebody's time in US is different? Then it impacts everything, right? So what BIPM does is it tries to put everything all the time together, right? So after we, like NMC in A-Star gets this accurate time, what we do is we disseminate this time to other sectors who needs this accurate timing information through NTP, which is called Network Time Protocol, right? So this timekeeping is not only keeping the time with us, but we disseminate this time to other who needs it, yeah.
So it's basically for time sensitive sectors, basically.
Yes.
Like the stock market and many
Yes.
others. All right.
Even stopwatch. So I can share you something like recently I got to know about this. So they have stopwatch. So stopwatch is used in different areas, like different people use stopwatch, right? So they even send that stopwatch to our lab to calibrate it against atomic clocks to see that how much difference is their stopwatch compared to us, no? But it's quite interesting because stopwatch do not need to be so much accurate for them, but then even though they want to know how much millisecond or smaller second difference they have in stopwatch. So yeah, they send those kind of things also for calibration. Yeah.
All right.
I want to go back to your PhD just for a minute here, because there's still something I think that we didn't explore, which is like once you have all the data collected, right? So it's just raw data, and you want to get to a forecast. You want to get to a prediction of some sorts. So what kind of algorithm are you following? Did you have to come up with a new algorithm, or was your work mainly revolved around improving current algorithms, and how do they work in general?
Okay, so for this, right, so once the raw data is there, as I told you that GPS technology for rainfall forecasting was 10 years plus, right? So there are already existing algorithms which is required to do prediction of, so I can put it like this. So we have raw data, then we have prediction of precipitable water vapor first, and then comes the rainfall. Okay, so this precipitable water vapor is how much water vapor content is in the atmosphere. All right, then we correlate this water vapor content with rainfall, right? So between this signal delays and precipitable water vapor, there are existing algorithms, or you can say software, things like that, to do this mapping, right? But my contribution here in this mapping was to improve one of the parameters in that existing algorithms. So what I did was I used the data from around 174 stations, because for these two, I don't need the rain data, because now I'm analyzing the water vapor content of atmosphere and the signals, right? So I don't need the later part yet. So for this, I used 174 stations around the world. So it includes tropical, subtropical, and temperate, all the regions, 174 GPS stations, and I improved the parameter, one of the parameters, to do this mapping, because the mapping function was already there, right? So I improved the parameters using the data, and then I published. And then after I get this water vapor content to the rainfall, it's all new. So it's one of my contributions as well. So this algorithm to do the prediction is somewhat region specific, because as you know that the rainfall pattern here and the rainfall pattern in some other countries in temperate doesn't match. It's completely different. It's season specific and location specific, right? So the algorithm, that later part was developed by me, and I used Python and MATLAB to develop the algorithm, and it was all based on data processing. Yeah.
Okay, I think now makes a little bit more sense. But okay, now again back to your current work. Does it involve still like your typical research activities where you have to identify certain challenges and you're trying to find ways to solve them, or is it more of a technical engineering work?
Actually, this part of the work at NMC has two sides. So one is maintaining the clocks that we have and disseminating the UTC time to whoever needs it, right? And another part is also R&D. So I coming to this field from my background of rain forecasting and weather and all. So one of the things I'm looking at is also how to improve the algorithm that is used inside this timekeeping and bring in the factor of weather. Bringing the weather factor in can improve the stability or not. So one of the things I'm looking at is also this. But still, it's in initial phase. I have to write for grants and get money, and then only I can go further about it. And one more thing I can add is if you have heard about sea level. So one of the things that all the coastal areas around the world are concerned is sea levels, because sea level is rising for like long time, right? So in Singapore also they are like concerned about the sea level, and they have NRF grants that they give to people who do research in the sea level area. So I'm also looking at how GPS I can use to correctly predict the sea level heights, because GPS, as we know, X by Z, right? So Z is the height factor. So mostly the height factor is very bad if you compare it with X and Y. So when you go with your GPS app, you can get X and Y very nice, but the height is always not so accurate. So it has the highest error. So I want to study like why this high error is coming. Is it from clocks? Is it from weather? Is it from what parameters? So I have to study all this to get the H factor improved so that I can apply it to national sea level projects. Yeah.
Okay, so you're now also using the same technology, the GPS, to work on sea levels and predicting rising sea levels. I want to go back to something you mentioned at the very beginning. Those new positioning satellites from China and from Russia. What's special about these new ones? Are they different from the old ones that were already up there?
No, the technique is the same, but the main difference that we have is we called Rhinex. So it's a bit technical. So it's receiver independent exchange files, right? So these Rhinex files are so-called transmitted whenever the signals are transmitted from satellites at receiver. They store the signals in so-called Rhinex observation files, right? So if you say GPS, then all the GPS satellites, they transmit same frequency band, and they transmit same bits of information, similar header, similar tail, and then the same information, just the delay things will change, right? But if you talk about Russian satellites or Beidou satellites, first of all, their signal frequency is different, and then their header and tail, everything is different. But given the differences, the thing is the same. The architecture is the same. The basic principle of how they work is the same. But only the differences is the technicalities. Like something is changing, this are changing. So it comes to us who do the data processing. For us, it's a little bit burden because you cannot use the same specific program to process your GPS data and to process your Beidou data, because they have some differences in their raw observation files. Yeah. Other than that, the basic science is the same.
So do you need the special devices to communicate with the different satellites? Because I think most phones already have a GPS GPS chip that is already integrated with the network chip.
Yeah, I think
it all comes in one package.
It's the same antenna. Just the range of the antenna should be within the limit. Yeah, because with the same device, like with the same GNSS, it should be said as GNSS receiver. If you said GPS receiver, then that receiver will not take the signals from other satellites because it's GPS specific, right? But if you have GNSS receiver, then it can take the signals from all the different satellites.
So the GNSS is the one with the larger band.
Yes, GNSS is inclusive of all the different satellites.
I see. And okay, so just speaking about weather forecasting, rainfall, rising sea levels, it sounds like it's kind of an impossible task. I mean, we've been trying our best tools, and every year there's a new research, new device. But at the end of the day, we do know like the whole system is chaotic and cannot be predicted for long periods of time. So where do you see, like, do you see us still improving to a great extent where we can predict things very accurately for like a week period of time, or do you see like just minor improvements on the efficiency of the systems? And where do you see this going in the near and far future?
For now, like weather forecasting using GPS is still a child, I think. I mean, it has a lot more to see before it's is like a foolproof system that can use things to predict, right? But over 4 years of my PhD, when I was doing it, I saw lots of community growing in this area. Because initially, I had really difficulty in finding a common conference as well. Because conferences, they have big topics like microwave, and inside that, I could never find like rainfall forecasting, and I'm not like my field doesn't come under meteorology, and it also doesn't come under triple E completely, because it's a mix of both, right? So it was really difficult to find conferences where you could meet people of the same area and discuss about it. But later, as progressed, I could see, because there is a conference called IGAS, which is about remote sensing, and this thing, what we are talking is also remote sensing, right? Because we are sensing water vapor of atmosphere, which is remotely done. So it's one of the category in remote sensing. And when I went there and met people of the same area, I could see that people are doing about it, people are doing things for it. But to be very real, I think it's going to take a bit of time before it comes there as a system. Yeah.
All right. I wanted to ask you, like, because weather prediction usually involves some kind of pattern recognition, like collecting a lot of data and then seeing some patterns and so on. So to what extent is AI and the advancements in artificial intelligence contribute to that cause, like to weather prediction in general, whether it's now or in the future, how it will be in the future? Yeah.
It's a very nice question. And I had this difficulty when I was trying to implement the machine learning algorithm to do the weather forecasting, especially for data from Singapore, because we do not have specific seasons. And those countries where there are specific seasons like autumn, summer, rainy, and dry season, it was a bit easy because you follow the same pattern all over the year, right? But here in tropics, the rainfall occurrence, I'm only talking with respect to rain, not with others. So with respect to rain, it was a bit difficult for Singapore data compared to the other regions' data with respect to the pattern. And other than that, after I used like temperature, rainfall, when I increased my input variables to my AI system, it kind of improved my results as well. But initially, with using the PWV data only, it has a lot of variability. It doesn't have a specific pattern as per se.
And during your research, your PhD and all that, have you also witnessed or heard about other interesting uses for GPS satellites? Because for us, this is like I've never heard of them being used this way. So, is there anything for you? Have you seen the GPS used for other things than positioning?
So, positioning and weather forecasting, and I think now Christopher might be familiar with this also, because his research is also one of the applications of GPS, but in ionosphere. So whatever I was talking was troposphere, right? So we have troposphere and ionosphere. So all the water vapor is here in troposphere. But now we are also looking at ionosphere. So using GPS signals to see how much total electron content, if I'm not wrong, TEC, is there in the ionosphere layer. So using GPS signal to see what's there in ionosphere. I think it's also interesting. And apart from that, I have to check also.
Okay, and just out of curiosity, do you know the specific frequencies that are used?
Yeah, 1.5 and 1.2 gig for
Gigahertz.
GPS. Yeah, not for others.
And the others, do they go higher or lower?
Similar range, but might be higher.
I see. Okay, so I guess 1 gigahertz, that already falls within the microwave range, right? And okay, so this data you're getting, I think we already maybe touched upon that, but just maybe just to clarify, the data you're getting, are you sure like it's not affected by any other radio waves in the atmosphere? Because now we have a lot of microwave, especially in the millimeter wave range.
Mm-hmm.
So is there any technique that you implement to filter out or how does it go?
So just now when you asked me about the frequency, I gave you two, right? So it's not the range, it's actually two frequencies that the GPS satellite sends in. So one of the things that we do is dual frequency dependent analysis so that we can filter out some of the other variables that's coming in. And another thing that's a big issue in GPS is multipath. So multipath as in the reflected signals, right? Because we are now in urban society. It's not like there's nothing around us. There are so many big buildings and things like that. So when the receiver is not on top of a building, it's like maybe on the road or something. Then the one problem is the visibility of satellite is already low. So from 8, you will be like 5 or 4 satellites, and out of those satellites also, those satellites will be reflected many times by the surroundings, right? So there is multipath effect. So when we do the analysis in our algorithm, the multipath should be corrected, and the signal to noise ratio also needs to be checked. Yeah, so both things has to be done before you verify that the raw data is correct or not.
All right. So as we approach the end of the episode, we always like to ask our guests about their personal interests outside of the research field. Yeah, the relax bit. Yeah. So if you can share with us some of your other interests beyond your research area, things you like to do in your free time, or you like to think about, or learn more about, etc. So if you can share with us some of those.
Yeah. So I can talk about this a lot. So when I was doing my PhD, as Ahmed knows, right, we have this EEE GSC inside our NTU EEE. So I used to be involved in that, and I made a lot of friends out of that, because apart from that, I used to be only in my lab, right? So there is a very bad culture in NTU that one person is only attached to one lab, like he or she doesn't go out of it, and then all the other things are blind, like doesn't know about anyone. But when I came into this EEE GSC, I made friends from all the different labs and all the different backgrounds, right? So it was quite nice, and I made nice friends who are still friends with me after my PhD as well. So it was very nice, and I used to hang out with them. And as a personal hobby, I also used to dance. I mean, I dance now also. So at that time also I used to dance, and yeah. So that's pretty much about it.
I know that you're also involved currently with the IEEE Singapore.
WIE. Yes.
Yes.
Not Singapore section, but Women in Engineering section of IEEE. Yeah.
I see. And how does that compare with your student activities in NTU?
So IEEE WIE is more professional. I mean, like right? So we were also students. Now we are becoming a bit professional. So we target like those industries where they would want women to be promoted, and then we would talk to them about some collaborations or bring in as speakers, and then we try to organize some events. So pre-COVID, it was very nice. Like we could do physical meetings and all, but post-COVID, all the things are just limited to webinars and speakings and talkings. Yeah, a bit boring, but yes. So I think we need to be involved in such clubs and make more friends so that PhD doesn't become so bored and like, yeah.
Yes.
Yeah, indeed, correct. I can also relate with that. With what you mentioned about like being stuck in your own lab and never going outside to see other labs and meet other people. Yeah.
Yeah, that's true. Is there anything you would like to share that we have not asked you about or didn't come up?
I think most of the things are done, but one thing that I personally felt during my PhD was your personal well-being. I mean, both physical and mental is very important, because I had touch wood. I was lucky. I didn't have any problem with my supervisors or with my lab mates, but I had friends who had problems with their supervisors or mentors, right? So I have also seen few cases whereby the conditions became so bad that people have to leave their PhD, right? Because of small misunderstandings. So I really suggest like those students who are doing PhD to make it clear from the beginning and make a very strong inner circle of friends, make very strong outer circle of friends, so that you get the emotional support from before. And if you have any problem, it's really important to talk it out and solve it in the beginning before it gets very worse. Yeah,
that is very important indeed. Well, thank you very much, Shilpa. That was a really interesting episode. And wish you all the best in your research career.
Thank you very much. Thank you.
Well wishes to all of you as well.
Thanks.
Thank you. Bye bye.